We'll start in 5 minutes. It seems like the lag is pretty severe. Seems like the lag is pretty severe. Yeah, no worries. Thanks for coming. Thanks a lot, man. Thank you very much. Yeah. Um, so today we'll try to do some actual math. Last time we were most just just talking about the books, the authors, which is interesting on its own. But today we'll hope to do some actual math. I've been posting shorts recently. If you guys have thoughts about those, let me know about them. So the idea is to spend as little time as possible to give a quick introduction on the topic, because sometimes I forget about these things. I would like to create a repo, so to say, for myself to refresh on some of the derivations and definitions. So yeah, I figured one short per day is more than manageable. So that's I'm planning to keep it up. And also today I published a longer video. It's about the t-distribution in mathematical statistics, which I found to be not very well known. I mean, of course, the t-distribution is well known, but what really is about, not so much. I've never seen on YouTube a similar video that explains those things, if I may say so. And also, I didn't find similar material on Wikipedia either. So I was really surprised, because YouTube, sorry, not YouTube, but Math Wikipedia is usually very comprehensive. As far as a public resource is concerned, is actually quite comprehensive. So this was the thing I posted about t-distribution was actually taught by a professor of mine, but apparently it wasn't that well known, and a lot of people seem to have the conception that the t-distribution is only derivable from the Gaussians, which is a misunderstanding actually. So go check out that video if you're interested in mathematical statistics. So yeah, we're about to start. All right, let's begin. So today we're going to keep reading Whittaker and Watson. So I'm planning to, the basic plan is to alternate, okay, between classical and modern analysis. I hope that's okay. But I don't want to make the alternation too frequent, because studying these things do require some sort of consistency. We don't want to forget about what we just seen last time, for example, because math is, of course, cumulative. So the idea is we're going to try to finish one chapter in one book, and then jump to the other one. So for example, I mentioned last time my plan is to cover both classical and modern analysis. I mean, I said cover, that's kind of ambitious. I'm holding the attitude of a student. Okay, I'm not trying to be the professor here, because really a lot of things in Whittaker and Watson, for example, I do not know very well. Okay, and the other resource we mentioned last time is going to be advanced calculus, based on the Harvard Math 55 class back in the 1960s. So that series is going to be a separate series called Math 55 at Home, which I think is kind of appropriate. As far as the exercises of this book is concerned, okay, so we're talking about Whittaker and Watson. As far as the exercise in this book is concerned, we will try to solve every single in-text exercises. Okay, in-text exercise, because the exercise for this book, so to say, actually is a very good practice to first look at where the exercises are in the math book before reading it in detail, because the exercises are kind of the heart and soul, so to say, of the book, because unless we can do mathematics, we don't really know mathematics, right? So, for example, this first chapter has actually very few exercises, which is a bit of a shame. I guess we can make that up, certainly, later down the road when we encounter modern analysis. But as far as Whittaker-Watson Chapter 1 is concerned, there's only a handful of exercises, which I haven't seen one yet. That's a bit weird. Yeah, so I think the only exercises are in the back. The miscellaneous examples. By the way, they're not called exercises, they're called examples in the old British traditions. Okay? The old British textbooks tends to call exercises examples, but they aren't really worked out examples like you would expect from a modern text, so to say. And for example, here, so these aren't considered in-text exercises. Okay, these are called miscellaneous examples, but we'll look at them. We won't just ignore them. All right. But let's say, for example, in Chapter 2, there's going to be in-text exercises. For example, here you have example 1. This is a rather simple problem. Actually, it is worked out, huh? All right. So we basically proving the sum law of the limit. Right. As you can see, it's not that crazy. Even though it's Whittaker and Watson, it does have basic questions. Right. And later we also have more exercises, I believe. Okay. But you get what I mean, because I don't want to have, let's say, one Cambridge triple question stopping us in the track. We don't want to go over the material because the idea is not to master every single question, is to obtain a working knowledge about the special functions in applied mathematics, right? So and a book like this is not designed to be read in just one pass, right? So if later we found some more thoughts and ideas about solving a particular problem we've seen earlier, which we didn't manage to do at our first reading, then by all means come back. Okay. All right, so that's enough about the logistics. Let's dive into the math. All right, so here, before we talk about complex numbers, we first need to discuss irrational numbers, which is actually much, much harder than complex numbers. Yeah, we all know how the numbers evolved. Okay, historically, first we have the whole numbers, the natural numbers. The whole numbers actually include 0. Okay, in analyst tradition, the natural numbers do not include 0. Okay, in an analyst tradition, big N, the set of natural numbers start from 1. If you include 0, you get the set of whole numbers, and then we have the integers, which also include the negative integers, okay, and then the rationals. Right, so these are all kind of straightforward, okay, and not that controversial, at least as far as the history of mathematics is concerned. But it's the jump from the rational to the reals turns out to be the most difficult step, because after you have the rational, after you have the reals, aka the rationals and irrationals, going into the complex field is actually very, very simple. Okay, so this is going to be a major section, section 1.2, Dedekind's theory of irrational numbers, is something that we're going to first, we're going to follow the flow of the author, and then we're going to reconstruct. Okay, because the language is rather antiquated. This was written before set theory became mainstream, and actually you can see the ideas of set. The author uses the words such as classes, an aggregate, right, as a replacement for the word set. Okay, this was before set theory was standardized. So we'll try to understand what the original exposition, and then try to reconstruct or rephrase into modern language. Okay, so this is actually, don't be surprised, we're going to spend a lot of time in this section, because unless you have seen the Dedekind theory, or at least one construction of the set of reals, I don't consider the person to really know analysis. Okay, Dedekind theory of irrational numbers. The geometric property of points on the line, which suggested the starting point of the arithmetical theory of irrationals, was that, okay, wow, if all points of a line are separated into two classes. Okay, we'll try to draw a little diagram on the side. Okay, separate the line, the points into two classes, such that every point of the first class is on the right of every point of the second class. There exists one and only one point at which the line is severed. Okay, so this is a very long sentence, but we'll draw a picture to get the idea. So imagine this is a real line. Okay, and here, let's imagine we put a cut, quite literally, on the line. Then we can see every point of the first class, this is the first class, so to say, later we'll give that a name, is first class is actually to the right. So yeah, so the first class is actually to the right of every point in the second class. Okay, so that's the very intuitive idea of separating a line into two portions, right? Sorry, this is I apologize. I'm not very proficient with the drawing board in MS Word. Okay, so and the point is, there exists one and only one point at which the line is severed. It is completely geometrically obvious, but we wish to formalize such ideas without making any explicit reference to geometry. So that's the purpose here. So we want to talk about irrational numbers without talking about irrational numbers. So it's kind of like the some interviews that you've seen on YouTube. Tell me where you're from without telling me where you're from, right? We want to define irrationals without, well, mentioning the irrationals. Following up this idea, Dedekind considered rules by which a separation, there's a dagger symbol, we'll look at that, or sections of all rational numbers into two classes can be made. These classes, which will be called the L class and the R class, or the left class or the right class, being such that they possess the following properties. My goodness, this is also a very long sentence. So Dedekind considered creating a separation of all the rational numbers. So imagine this is the line here only represents Q. Okay, that's the set of rationals. We don't have the reals yet. Okay, so we want to separate the Q's into two parts, the left class and the right class. Okay, at least one member of each class exists. At least one member of each class exists. I'm not sure what that means. Is that a member of, meaning does that mean a class is not empty? Is that what it says? Okay, let's keep reading. Every member of the L class is less than every member of the right class. Okay, so basically, if I dare to translate to modern terms, one is said at least one class is not empty, right? And The second is very intuitive. It is obvious that such a section is made by any rational number x, and x is either the greatest number of the L class or the least number of the R class. Okay, so if, let's say, the cutting position corresponds to a rational, then the rational can either be the greatest element of the left class or the least element of the right class. Okay, so this makes sense. Okay, and we'll come back to the footnotes later. Or the least number of the R class. But sections can be made in which no rational number x plays this part. Section can be made in which no rational number plays this part. Yes, that's the classic square root of 2 example. Thus, since there is no rational number whose square is 2, it is easy to see that we may form a section in which the R class consists of positive rational numbers whose square exceeds R, and L class consists of all the other rational numbers. So in this Dedekind's theory, okay, so imagine if we wanted to talk about square root of 2. What is the square root of 2 in Dedekind's theory? Well, R is equal to x in the set of rationals such that x is positive and x squared is greater than 2. Okay, that's a description of the R class. And the left class is simply, well, Q minus R. I'm using the set difference notation here. Okay. So it certainly makes sense to describe one irrational number, square root of 2. So the square root of 2 in Dedekind's theory is an ordered pair. Is an LR, like that. Okay, but of course we aren't interested in just defining one irrational number, right? So how do we generalize this? Okay, before we read the next paragraph, let's take a look at the footnote that we missed. Dedekind, star. The theory, though elaborated in 1858, was not published before the appearance of Dedekind's tract. I don't know German. I guess I suppose this is irrational number. If anybody knows German, please let me know. I mean, I'm not too bothered with Google translating this right now. Okay. Other theories are due to Weierstrass and Cantor. I wonder what's the approach Weierstrass take, because in modern analysis, okay, the two most celebrated approaches for a constructive definition, I'm using the term loosely because a constructivist certainly would not agree. Okay, a constructive definition, I mean non-axiomatic definition of the real numbers, are our most popular ones are Dedekind cut, which we're reading right now, and Cantor's construction. Cantor's construction is called equivalent classes of Cauchy sequences. Okay, I wonder what the approach that Weierstrass took. Anyway, this is not our main concern right now. There's a dagger sign which says Dedekind considered the rules by which a separation. Okay, this procedure formed the basis of the treatment of irrational numbers by the Greek mathematician in the 6th and 5th century. Wow. The advancement made by Dedekind consisted in observing that a purely arithmetical theory could be built upon it. I see. Okay, so this is really just an ancient idea that was revived in the 19th century. Okay, good to know. Anyway, let's continue. Then this section is such that the R class has no least member, then this section, okay, it means a section whose boundary, so to say, is not a rational number, right? So before we see that if the section is made by any rational number, the rational number is either the greatest number of L or the least number of R, right? So here we're only interested in the section in which the R has no least element, no least member, and L class has no greatest member. Okay. 4. If x be any positive rational fraction, and y, okay, what is this? What is this y? I think we have some work to do here. Okay, so okay, what's the purpose of this expression? 4. If x be any positive rational fraction and y is equal to this rather arbitrary formula. Of course, there should be a method in the madness, but let's just keep reading. Y equals to x times x squared plus 6 divided by 3x squared plus 2. Then y minus x is equal to 2x times 2 minus x squared. I think this is just basic simplification, so not much else is going on here. Y minus x. And y squared minus 2. Y squared minus 2, I think, yeah, this is probably once again just simple algebra. So the point is, it seems like, so x squared, y squared, and r are in order of magnitude. So I guess y minus x is positive. No. Okay. I think we have to write things down. Okay. Let x be any positive rational. Okay. And y is defined as this weird expression. Okay. Okay, y minus x. I will just take the. Actually, you know what? Let's verify this algebra as we should do always. Okay. Okay. This is y minus x. Let's verify this simple algebra. Because you never know. Something might go wrong. X squared plus 6 minus 3x squared minus 2. Okay, so this x times 2 minus x squared over 3x squared plus 2. So what does this mean? X is positive, and of course 3x squared plus 2 is positive. So that means y minus x and 2 minus x squared have the same sign. So let's write that observation down. Y minus x and 2 minus x squared have the same sign. I think that's part of the rationale of this construction. And then y squared minus 2. Y squared minus 2 is what? Y squared, oh wow, the algebra gets a little bit ugly, but we'll handle that. X squared plus 6 squared, and then 3x squared plus 2 squared. This is y squared minus 2. All right. It does not seem like there's things that can be factored, so we'll just do things by brute force. Sorry, that's my WeChat. not your phone. So x quad plus 12x squared plus 36. Just expanding this out. Okay, minus, I'm running out of space here, but just finished writing this line. 2 times the bottom squared, get 9x to the 4th plus 12x squared plus 4. That looks about right. Okay, and then 3x squared plus 2 squared. Okay, wow, that's a mess. Hopefully we'll get the result that the book promised. Okay, so here we have x to the 6 and 12 times x to the 4th. But we also have minus 18x to the 4th, so that's minus 6x to the 4th. Okay, and what about quadratic terms? There's no odd powers. We observe that. So x squared is going to have a coefficient of 36 minus 2 times 12. So that's 36 minus 24, so minus 12 x squared. Okay, and then minus 8. Okay, and then 3x squared plus 2 squared. Okay, so we can rewrite the numerator as such, x to the 6 minus 6 is 6, we can write it as 3 choose 1. I'll use this notation for the for the binomial coefficient. 3 choose 1, C 3 1. Okay, in a lot of books in the Anglo-American tradition, they write n choose k, but I'm not a huge fan of this notation because it takes too much space. You know what I mean? It takes 2 rows. I was like, for no reason. So I like to use this when I studied this in high school in China, actually. So we use this notation for the binomial coefficient. Okay, no offense. I mean, it's just different habits. All right, x to the 4th, and then minus. Did I make a mistake? I think I made a mistake. This should be plus. Plus c choose C3 2 x squared, and then times 2 squared, and then minus 3 to the 2 to the 3. Okay. It should be plus. Yes, you caught that. I just changed that. Good catch. Because when I was trying to get the factor out, the combinatoric, and I've spotted that mistake. Yeah, thanks for pointing that out. Yeah, I made the mistake when I was first doing that. Okay, and divided by the denominator. Yeah. Okay, so this is indeed a binomial expansion. So we get x squared minus 2 to the 3rd divided by 3x squared plus 2 squared. Okay. Okay, so what does this calculation stand for? Okay, what is the meaning of this? Why do we care about this? Rather tedious steps. Well, y squared and 2, therefore y squared and 2 has the same sign with what? Imagine if y squared minus 2 is positive. That means x squared minus 2 is positive. So therefore, and also vice versa, right? If y squared minus 2 is negative, because it can never equal to 0. x and y are both rationals. Y is a rational as well. Neither of their square can be 2. So either has to be strictly positive or negative. Here we see that y squared minus 2 and x squared minus 2 have the same sign. Okay. So, and also y is positive as well. So that means x and y are both positive and must be on the same side. Okay, this is the square root of 2. We can talk about square root of 2 now because we just defined it as a cut. Okay, so this symbol is now legal. X and y must be on the same side of the square root of 2. So that's the purpose of this calculation. And what? And also x minus y minus x have the same sign as 2 minus x squared as well. So imagine if, let's consider 2 cases. Case 1, y is greater than x. Then y minus x is positive, and thus 2 minus x squared is positive. 2 minus x squared is positive, that means x is in the left class. Right? So x is here, and y is greater than x. So that's case 1. In case 2, if y is less than x, well, that means y minus x is negative. Well, y minus x is negative, that gives us 2 minus x squared is negative. 2 minus x squared is negative, that means y, x squared minus 2 is positive. That means y squared minus 2 is positive. Okay, so that's case 2. We have y is less than x, and x and y are both in the right class. So x is here, y is here. That's case 2. So the point of this rather contrived arithmetic is that it is possible that if we pick any number in the left class, you can find another rational number that's greater than x. Right? If you pick any arbitrary number x in the left class, you can find the number y that is greater than it, and it's still in the left class. It sits between x and the square root of 2. Well, on the flip side, if you pick an arbitrary number on the right class, you can find another rational that is less than x, whose square is also greater than 2. So that's the explicit construction. Okay, so if we just summarize what we just did as a formal theorem, okay, if x is less than y, let's say if x is positive, okay, if x is positive and is in the set of rationals, okay, with x squared less than 2, then there exists y in Q such that y is greater than x and y squared is less than 2. That's the first part of the theorem. The second part of the theorem says if x is greater than 0 and is in Q with x squared greater than 2, okay, then there exists y, in Q such that Look at the picture. Y is less than x, and y squared is greater than 2. Period. That's the formal theorem. Okay, so in the proof is one line, Whittaker and Watson style. Let y equals to this weird fraction. Okay, it's quite ingenious, if I may say so. Of course, this is a classic. Dedekind's original essay is still recommended for anybody interested in the history of mathematics. 3x squared plus 2, that's the denominator. And then you have x times what? X times x squared plus 6. That's the proof. This proves existence. And the rest is just computation, which we just did. That's the proof. Okay. Anyway, I think we can move on. Okay. So x squared, y squared, and 2 are in the order of magnitude. I see what it means. I didn't get it. It means x squared is in the order of actually, based on our picture, it should be x squared and either x squared is x squared less than y squared less than 2, either that, or 2 is less than y squared less than x squared, right? I think that's what it's trying to say. I'm just not very familiar with the language here. And therefore, given any member of x in the L class, we can always find a greater member of the L class. Yes, that's the y. Or given any member x prime of the R class, we can always find a smaller member of the R class. Also y, such numbers being, for instance, y and y prime, where y prime is the same function of x as y of x. I think we fully understand what this paragraph is saying. All right. So if a section is made in which the R class has a least member A2. Okay, so let me just try to draw a picture here. So R has a least member. I'll use the closed interval notation. Okay, this is A2. The R class has a least member A2. Or if the L class has a greatest member A1. That's the picture, A1, the L class. The section determines a rational real number. Okay, so that's a rational real definition, the definition of a rational real, which it is convenient to denote by the same symbol, A2 and A1. If a section is made such as the R class has no least member and the L class has no greatest member, the section determines an irrational real number. Okay, so now we have the formal definition of a rational real and irrational real. It's all based on the properties of the two pieces of the cut. Right? Okay, if x and y are real numbers defined by sections, we say that x is greater than y. We say that x is greater than y if the L class defining x contains at least 2 members of the R class defining y. Contains at least 2 members. Why 2? Okay, so here this is very subtle. This is very subtle. So we're now, after defining what the real numbers, aka sections, look like, we're now trying to establish relations among them, right? So here we're trying to compare two real numbers. We say x is greater than y. So the intuition is of course, x is to the right of y. If the L class defining x contains at least 2 members, why 2? 2 members of the R class defining y. Why can't it just be 1? Because let's imagine this example. Let's say, how do I define 1? How do I do? 1 is of course rational. 1 is of course rational. So the L class can be, right now I'm writing intervals to denote only the sets of rationals. Okay, so if I write minus infinity to 1, that's the set of rationals less than or equal to 1. Okay, so if I want to be extra careful, I put a little q in the subscript here. So this is L, and the R is of course 1 to infinity. Okay, that's one way to define 1. Of course, another way to define 1 is minus infinity to 1 open interval. Once again, this stands for all the rationals strictly less than 1, and R goes to closed interval 1 to infinity. As you can see, the first left class has exactly one more element than the second left class. Right? But of course, we don't want to say this is one section. Okay, this is one real number. This is another real number. We don't want to say the first real number is greater than the second real number. They should be the same. But if you have two members, if the L class defining X contains at least two members of the R class defining Y, then such ambiguity is removed, right? So if you have two, yeah, so this is very subtle. Okay, we'll take that for, I mean, we'll respect the original, okay? We'll let the authors communicate, and then let's see how we can simplify this. Okay. They're certainly correct, okay? It certainly makes sense. Okay, so I'll just try to remove this scribble. Everything will be more polished after polished in our own notes after reading it. Okay. So let alpha, beta, and so on be real numbers. That means these are cuts. Okay, these are cuts. Alpha, beta. Do not think of them as a single point. Think of them as ordered pairs. As ordered pairs of classes. Alpha has a left class and right class. Beta has a left class and right class. And let big A1, big B1, and so on be any members of the corresponding L class. Be the corresponding L class. Be any members of the corresponding L class. I guess A1 is a member of the left class of alpha. B1 is a member of the left class of beta. Right? So that's the notation here. While A2 is a member of the right class of alpha. B2 is a member of the right class of beta. Okay, so the classes of which A1, A2 are respectively members are the classes of which are respectively members will be denoted by the symbols. The classes of which, wow, this is a tricky sentence. How do we make sense out of it? So imagine, let's say I have a section. I have two classes for alpha, so to say, L and R. So here I have A1, which is in the left class, and A2, which is in the right class. The classes of which A1, A2, and so on are respectively members will be denoted by the symbols A1 bracket, A2 bracket, and so on. Does that mean A1 is just L? A1 bracket is just L? Is that what it says? The classes of which A1 is member will be denoted by the symbol A1 bracket. I'm not sure. Okay, let's just say I'm not sure. It's okay. We can keep reading and determine what exactly this means. Okay. Then the sum, written alpha plus beta. Okay, so now we're trying to define the sum of two real numbers. Once again, in terms of sections. Right? We just defined the notion of order. We just defined the notion of order. X is greater than Y. Using sections. And once again, as a personal aesthetic choice, I'm not a big fan of the notations here, because if we use Latin letters as real numbers, why do we switch to Greek letters? Okay, so once again, we're not here to criticize the author. Okay, once again, we're not trying to do that. We just wanted to foster the habit of critical thinking, because this might cause confusion later. Okay, something we just need to be mindful of. Here, x and y are real numbers, which are sections. Alpha, beta are real numbers, which also mean sections. Okay, these are the same kind of objects. So here, let's try to define the sum of two reals. The sum of two reals, alpha and beta. How do we define that? Of two real numbers, alpha and beta is defined as the real number, rational or irrational, which is determined by the L class A1 plus B1 and A2 plus B2. I think now the notation makes sense. So in modern set notation, so you have alpha equals to L alpha, right, R alpha, so to say. That's an ordered pair. And beta is equal to L beta, R beta. How do we add them? Well, you add L alpha to L beta. I'll say more on this. R alpha plus R beta. Where the notion of the sum of two sets is defined as follows. So if S and T are sets, meaning subsets of rationals, then S plus T is simply the collection of S plus little t, such that little s comes from big S and little t comes from big T. This is what it means when it comes to the sum of two reals. Okay, so now we have order and we have the sum. Okay, and this is, of course, the very beginning. This is, of course, the very beginning of this theory. We still need to verify the usual properties of, say, transitivity of inequality holds for the order relation, right? And also we need to verify that, for example, addition satisfies commutativity. All those familiar properties needs to be verified separately, right? In order to confirm that this is really working as intended. Okay, but now at least we have the definition of the sum. So, and we understand this notation, which is good. Okay, so it is of course necessary to prove that these classes determine a section of the rational numbers. What is that? Did we? Oh, yes. Of course, necessary. These classes determine a section of the rational numbers. It is evident that A1 plus B1 is less than A2 plus B2. I think this means that every number in this set, A1 plus B1, sorry, a1 and b1 are rational numbers, so this is not set relation. This is just number, the number a1 plus b1 less than a2 plus b2. Okay, and that at least one member of each of the classes, at least one member of each classes a1 plus b1 and a2 plus b2 exists. Okay, so why is it evident? Why is it evident? Well, hang on. Why is that evident? A1, the classes of which A1, because A1 is in the left class, A2 is in the right class, right? So A1 is less than A2, and B1 is less than B2, of course. So if you add the two inequalities, A1 plus B1 is less than A2 plus B2. Okay, this makes sense. It is indeed evident. Okay, and the two, and at least one set is not empty. Okay, yeah, this is also evident. It remains to prove, because if let's say one set, if let's say two sets are both empty, if let's say both sets are empty, that must mean the class, hang on, if let's say one of the two classes are empty, a1 plus b1 and a2 plus b2, let's say they're both of them are empty, what do we get? Well, we can either have a1 and a2, the bracket a1 and bracket a2 both empty, or b1 bracket or b2 bracket both empty, which are impossible, right? Both are impossible, because these are cut. In cuts, at least one class must be non-empty. Okay, so it remains to prove that there is at most one rational number which is greater than every a1 plus b1 and less than every a2 plus b2. What do we need that? What do we need to show that? Of course, necessary to prove that these classes determine a section of the rational numbers. One rational number which is greater than every a1 plus b1, less than every a2 plus b2. Okay, so this is the class A1, this is the class A2, okay, this is the class B1, and this is the class B2. And if we add them, okay, we get a class A1 plus B1 and A2 plus B2. Okay, we need to prove that there is a rational, at most, okay, this is crucial, because if the location of the cut is irrational, such a point might not exist. But if it exists, there can be only one, right? So that means it says at most. So if there's no such irrational number, that simply means the new cut A1 plus B1 class and A2 plus B2 class determines an irrational number. If there is one, that means it determines a rational number. Okay, so it remains to prove that. So how does it perform such a task? Suppose, if possible, there are two. Okay, this is a proof by contradiction. Suppose there are two x and y, with y greater than x. Let little a1 be a member of big A1. Okay, little a1 is here. Little a2 is here. Okay, and let n be the integer. Let n be the integer. Wow. This is, again, a very common experience when reading analysis book. You don't know how on earth did the author figure out such a condition, right? You often see, like even in modern analysis book, let epsilon greater than 0, let choose big N such that what? You don't know. You don't know how they got this choice, but you can verify it. Okay, you can verify it. But in order to really appreciate how such option was taken, there's got to be some kind of scratch work that was done. Okay, so imagine we have a1 and a2 as such, and let n be the integer greater than a2 minus a1 divided by 1/2 y minus x. Okay, so y and x are two, x and y are two numbers, x and y are two numbers that is greater than every a1 plus b1 and less than every a2 plus b2. Okay, so it's time to, I think, to put down some of our own notes, otherwise we'll get lost real soon. Okay, so this is a proof for the well-definedness of the addition operation, right? So this is class A1, this is a class A2, this determine alpha, that's a real number, and this is beta. I'll just reproduce the graph, the diagram once again. Okay, so we like to say if you add them, we get a new cut called alpha plus beta. It's just pure symbol. Okay, and on the left we have a1 plus b1 class and a2 plus b2 class. In order to prove this is a well-defined operation, that is, we do in fact get a cut, we have to prove there exists at most one rational such that one rational, let's say x, such that x is greater than a1 plus b1 for every a1 plus b1. Once again, this is non-standard notation. We don't do arithmetic inside a quantifier. Okay, that's not acceptable by modern standard, but we'll try to follow the text, just because that's what literally the text is saying. Right? X is greater than every a1 plus b1, and x is less than every a2 plus b2. All right. So prove by contradiction. Suppose there are two. Okay, we'll try to follow the construction here. So what's going on? Suppose for a contradiction, that we have two such numbers with y greater than x. There exists y and x in Q such that y is greater than x, and well, y and x both satisfy these two properties. So we have x is greater than a1 plus b1 less than a2 plus b2, and y is greater than a1 plus b1 and less than a2 plus b2 for all a1 plus b1 and a2 plus b2. Okay, so that's our assumption here. So now let A1, let little a1 be in big A1, and little a2 to be in big A2, and let n be the integer greater than, okay, let n pick big N in the set of natural such that n is greater than a2 minus a1. I hope my writing is still somewhat eligible. If anybody cannot understand what I'm writing, please let me know. I'll try to be as organized as I can, because later on we'll try to recast everything into modern notation and language. Okay. But the insights is still timeless. Okay, n is greater than this. Take the last of the numbers. Take the last of the numbers. Okay, so this is a finite sequence. A1 plus m over n. A1. Okay, so let's just try to figure out what is happening here. So imagine there is the situation which we assume for the sake of contradiction is as such. So there is a x and y. Y is strictly greater than x, and x is strictly to the left of all the a1 plus b1. Okay, and y is strictly greater than all the y is strictly less than all the a2 plus b2. Okay, so now imagine we have this big N, which of course exists. You can pick N large enough so that this inequality is satisfied, and take the last of the numbers a1 plus m over n, a2 minus a1. So this is an arithmetic progression with well, it starts from m equals 0, which is just a1, all the way to if you let m equals to big N, you get a2, right? So this is the arithmetic progression that runs from a1 to a2 with equal spacing. Take the last of the numbers of, take the last one, isn't that just a2? Right, that the last number is just a2, no? But apparently it says it belongs to a1. The last number of these which belongs to a1, okay, which we don't know what the exact index is, but we suppose, but there must be such a number, right? So remember, this is the cut for alpha, or a1, a2. So a1 is here, a2 is here. So we construct a arithmetic progression with finitely many terms that start from a1, that ends in a2, equally spaced in between. So somewhere in for some m, right, there's got to be this transition critical index where the number jumps from a1 to a2, which belongs to a1. So we're picking the last member. The last member. Okay, it must exist because it's a finite sequence. Belongs to a1, and the first of them belongs to a2. Take the last members. Okay, so the last member is this one. The first member is this one. Let these two numbers be c1 and c2. So they have to be consecutive. Right? They have to be consecutive. So c2 minus c1 is exactly the gap between the members in the arithmetic progression. So c2 minus c1 is equal to 1 over n, a2 minus a1. Ah, here comes the choice of big N. Okay, so here we see the motivation for choosing this big N. Because big N is greater than a2 minus a1 over 1/2 y minus x. This thing this difference, C2 minus C1, is less than 1/2 y minus x. And so let's see what we have done. Y is strictly greater than x, and x is greater than all of a1 plus b1, everything in a1 plus b1. Y is less than everything in a2 plus b2. And yet we have two numbers from, and we have two numbers, one from big A1 and one from big A2, whose gap is less than the half of 1/2 y minus x. Does that mean x cannot be greater? Yeah, so here you see x is, so that means C1 is here, C2 is here. C1 is here, C2 is here. So x is less than C1. C1 is in A1. That's not possible, no? C1 is in A1. X has to be greater than everything in A1 plus B1. Because C1, if C1 is in C1 is in A1, I'm struggling to see the contradiction. Let's see. Choose D1, D2 in a similar manner in the class defining beta. Okay. So hopefully we can write that ourselves. Okay, let's repeat this process and see how do we define beta. How do we define D1, D2? Okay, it's similar, so it's a good exercise for us. How do we define D1 and D2? Well, here we first need to pick B1 as a member of big B1. Okay, defining the two numbers D1, D2. The step is as follows. Okay, so let little b1 be in big B1, and let little b2 to be in big B2. Okay, and then we're going to pick big N greater than, similar motivation as we had earlier, B2 minus B1. Let's call it big N star, okay? And N prime, or so to say, N prime. 1/2 y minus x is entirely similar. We should be able to reproduce this procedure. Okay, and this is our big M prime. And then let's consider the let's write let C1, C2 be members of the set B1 plus M over big N, B2 minus B1, where M runs from 0, 1 all the way to big N, such that C1 is the greatest member belongs to big B1, and C2 is the least member, belongs to B2. This is C1 and C2. This is D1, D2. Okay, D1, D2, D1, D2. Then we have D2 minus D1, which is equal to 1 over N b2 minus b1. But big N prime is chosen in such a way, so this is less than 1/2 y minus x. Okay, so we have the inequality for C1, C2, which is here. This is 1, inequality 1, and this is inequality 2. If you add them together, we get this. So we have C1 C2 minus C1 plus D2 minus D1 to be less than y minus x. Okay, so therefore this is the same as saying C2 plus D2 minus C1 minus D1 is less than y minus x. Well, C2 and D2 comes from the A2 and B2 class respectively. Okay. So C2 plus D2, so that C1 plus D1 is here. And as you can see, this is a clear contradiction because x is supposed to be greater. So C1 plus C1 plus D1 is this point, C2 plus D2 is this point, and x and y is supposed to be greater. X and y is supposed to be two rationals such that x is greater than all the members from A1 plus B1, but we just found one that violated that condition. So I know, yeah, this is difficult. This is by no means like a trivial thing. This took mathematicians 2,000 years to clear this mess up. Okay, so it's very natural that we might not be following the logic of the first reading, but I think we did a pretty good job, no? If I may say so myself. So this is the proof by contradiction, and let's finish the reading. It says, but C2 plus D2 is greater or equal to y. C1 minus D1 is less than or equal to x. Yes, that's the supposed condition, right? So we suppose that y is less than or equal to all the members in the big A plus big A2 plus big B2. So this is supposed to be the case according to the assumption, and therefore we have a contradiction. Okay, so there cannot be two rational numbers that satisfy these two conditions. Okay, there's at most one. Okay, so that means if we add two cuts, we indeed get a cut. This operation is well defined. So basically what we just proved that in modern language that the construction by Dedekind satisfies closure under addition. Well, that's one of the most basic properties of the field, right? Field needs to have addition on it, among other things, and addition needs to be closed. What we just did is prove that addition is closed by this definition of Dedekind. Okay, so addition defined here is indeed closed. All right, and then let's see. I think here we should write a QED symbol here. Okay, just to be clear. Here we proved the closure of addition. If every rational number belonged to either the class A1 plus B1 or the class A2 plus B2, if every rational number belongs to either to the class A1 plus B1 or to the class A2 plus B2, okay, then the class A1 plus B1 and A2 plus B2 defines an irrational number. Why is that? Why is this sentence true? If every rational number belongs to either the class A1 plus B1 or to the class A2 plus B2, then the two classes define an irrational number. I try to find an example that violates that because it's not obvious to me. Belongs to the class A1 plus B1 or the class A2 plus B2, then the two classes define irrational. This is not obvious to me. So let's say I'm going to do something silly. So A1, once again, denotes, this is an interval of rationals. A1 is minus infinity to 0. This is my WeChat, not your whatever. Okay, B1 is 0 to infinity. A1 is minus infinity to 1. Okay, this is A2, sorry, A2. And B2 is 1 to infinity. Okay. So if we add A1 and if we add A1 to A2, what do we have? If we add A1, so this is one cut, this is another cut. So this is the rational number 0, this is the rational number 1. We add them, we should get 1. The set A1 plus the set A2 equals to minus infinity to 1, I believe. Yeah, and it's the open interval. Okay, and B1 plus B1 plus B2 is equal to 1 to infinity. Yeah, actually, is it, yeah, one can be obtained. One can be obtained. I was worried about whether or not one is attainable. Here we have 0 belongs to B1 and 1 belongs to B2, right? So 0 is obtained, 1 is obtainable for this interval. So this is our sum according to the definition. Every rational number, it belongs to either here or here. But this is the cut for 1 again. How is that a irrational number? Okay, I might be missing something really obvious here, but this is where we need to put a symbol of that indicated that we were struggling here, because this sentence it seems to be false, if I may say so. Most likely it's my own misunderstanding, but this is certainly weird. Okay, let's save that. Save the. Okay, I might need to come back to this later. Okay, if one rational number x exists belonging to neither class, then the L class formed by x, and if one rational number x exists belonging to neither class, so this is supposed to be the proof of this statement. If one rational number x exists belonging to neither class, then the L class formed by x, the L class formed by x, and A1 plus B1, and the R class A2 plus B2 define the rational number x. In either case, the number defined is called the sum alpha plus beta. Okay, this is apparently not a proof. It's just further explaining the outcome of addition. The difference is defined by the L class A1 minus B1, A1 minus B2, and the R class A2 minus B1. Okay, so apparently here the difference can also, notice that the difference in when defining the difference, the index got mixed up, huh? Alpha minus beta. When defining the difference, why is this A1 minus B2? And the R class A2 minus B1. So we're subtracting, so let's say this is alpha, A1, A2, beta, B1, and B2. So, okay. So we want everything to the left to be smaller, right? So we use A2, the smaller set, okay? Meaning the set whose numbers are smaller, A2, minus the bigger set. That's subtraction. So this difference is the new left class. Okay, and the new right class, because we want everything in the right class to be bigger, right? So we choose the bigger set in the bigger of the two sets, A2, minus the smaller of the two set for beta, which is B1. Okay, so that sort of makes sense. That's the difference definition. The product of two positive real numbers are defined as the product of the two R class and the product of the two left classes. The reader will see without difficulty how to define the product of negative real numbers. The negative numbers are a bit more bothersome, and the quotient of two real numbers. Okay, I think this is left as an exercise. And further, it may be shown that real numbers may be combined in accordance with associative, distributive, and commutative laws. Well, it is not shown here. So there's a lot of work left undone. Okay, I guess this is only a sketch of the theory. So, but still, there's a lot of detail to be filled in, for sure. The aggregate of rational real and irrational real numbers is called the aggregate of real numbers. So here we define the set of reals. For brevity, rational real numbers and irrational real numbers are called rational and irrational numbers, respectively. Okay. Okay, so that's the full section, 1.2. This is undoubtedly a very difficult section. So how do we reorganize everything? Okay, how do we reorganize everything? That's just done. Okay, so first there this definition of the cut. Okay, and then we defined various operations on the cut, between the cut. Okay, namely order and arithmetic. But there's a lot of properties we wish to verify in order to make the whole theory tick, right? Because let's be honest, at the end of the day, nobody think about the real numbers in terms of Dedekind's cut. Right? We don't do that every time we evaluate an integral. The purpose of Dedekind's theory is to establish that the usual rules for manipulating the real numbers are not self-contradictory. That's the whole purpose. Because after we've shown that such a set on which the usual arithmetic and the comparison laws hold, okay, we can simply work with these rules and forget about the underlying set. Right? So for a modern presentation, we need to first clarify what are the properties that we want and how exactly does the Dedekind cut fulfill them. right? So that's our objective here. So we're first going to write down our wish list, so to say, and then reconstruct the theory of Dedekind's irrational number, or real numbers, and see those items on the wish list are indeed satisfiable. So that's the plan. Okay, so let's switch to a modern perspective. I'll be as thoroughly as possible when I'm writing my it's not my own exposition, okay? It's still heavily borrowed from the classes that I took and taught. So hopefully I can do this by myself. Okay. So I think we had a basic idea what the Dedekind's cut is about, right? But still, it's important that we set things straight, because this is really the cornerstone of analysis. Okay, so starting from a modern perspective, so what do we want? Definition. Let's first define which way is easier. So should we define order first? Order is the easiest. Definition. Let S be a set. Okay, this is not necessarily a set of numbers. Let S be a set. We wish to define order on S. We wish to define order on S. So in an order, use the symbol less than on S, is a relation. And just to recall the basics, what is a relation? A relation is a subset of the Cartesian product. Recall that a relation R on a set S is a subset of S times S, the set of all ordered pairs. Okay. So that's a relation. An order is a relation. And we want the usual order properties to hold. So an order less than on S is a relation such that 1, we have the trichotomy property. If X is in S and Y is in S, then exactly one of the following is true. One of the following is true. Okay, X less than Y, X equals to Y, or Y is less than X. So we want this to hold. Okay, and second, because we didn't talk about how exactly you would compare the two elements on S. We didn't talk about it, but we wish that whatever order we end up picking should have these properties. Okay, so that's the first one. The second one, we want the transitivity to hold. So if X and Y and Z is in S, for all X and Y and Z in S, if X is less than Y and Y is less than Z, okay, then X is less than Z, the transitivity property. We want that to hold as well. So that's our definition of an order, axiomatic definition of an order. A set equipped with an order is called an ordered set. set equipped with an order is called an order set. Okay. So now we want to have a completeness statement for real. Okay. In modern terminology, it's called a completeness statement of real. Since we started from defining order, we will define what is an upper bound, what is a lower bound, what is the least upper bound, and all of that. Okay. So on an order set, or is it let E be a subset of an ordered set S. So let's suppose let S be an order set. Now I want to define the upper bound and lower bound for E. Okay. If E is, let's say E is set to be bounded above. Bounded above if there exists, say, a beta in S such that, I don't understand the math we're doing, maybe it's on the high level of studying, but I love your way of teaching, make the work, keep up the work, Mr. Okay, thank you very much, thank you very much. So, yeah, if you don't understand something, please try your best to just say, okay, stop right here, okay, retell the story or something. Okay. Okay, so I hope there's a little point of me just talking to myself. Okay. So I'm trying to voice my own confusion when I was studying this stuff, and at the same time try to be as clear as possible. Let S be a subset of an ordered set S. S is said to be bounded above. All right. If there exists a beta in S such that beta is greater or equal to, beta is greater, actually we haven't defined the notion of greater or equal to, so the notation beta, let's say x is less than or equal to y, means x is less than y or x is equal to y. Okay, so now I can talk about greater or equal to, such that beta is greater or equal to s, little s for all little s. Actually, I need to define for little s in big E. E is said to be bounded above. If there exists beta such that beta is greater or equal to s for all s in big E, in which case beta is said to be an upper bound of E, an upper bound of E. Okay, I didn't guarantee a set must have an upper bound. I didn't guarantee that a set must be bounded above. But if this is true, beta is said to be an upper bound of E. Okay, and you can define lower bound in a similar way. E is said to be bounded below if there exists, say, alpha in big S, such that alpha is less than or equal to s for all s in E, in which case alpha is said to be a lower bound of E. Okay, so hopefully everything is well defined. All right, so that's the definition of order, an ordered set, an upper and lower bound of a subset subset of a ordered set. Okay, and then we can talk about the supremum or infimum, the least upper bound, the greatest upper bound, the greatest lower bound. Okay. So if E is bounded above, which means it has an upper bound, and if E is an upper bound, suppose E is suppose E is bounded above. Okay. Suppose there exists alpha in big S. E is once again a subset of S. Is bounded over. Suppose there exists alpha in S such that 1. Alpha is an upper bound of E, and second, for every other upper bound, did I use beta? I should use beta, sorry, because I use beta for the upper bound. If beta is an upper bound, if for every upper bound, say beta prime, just the notational consistency, for every upper bound beta prime of E, beta prime is greater or equal to beta, then beta is called the least upper bound, or the supremum of E. Then beta is called the least upper bound, or the supremum of E. Okay, notation. Beta is equal to the sup of E. Once again, I didn't guarantee the existence of such things, right? Suppose there exists. If that's true, then we call that the supremum. Okay. Well, you can flip everything and define the greatest lower bound. Okay, just need to change a few keywords. Suppose now E is bounded below. Suppose there exists a alpha such that alpha is a lower bound. Lower bound of E. Okay. And for every lower bound, alpha prime of E. Alpha prime is less than or equal to alpha. So that's the greatest lower bound. Okay, so when we're writing these words, it's always important to keep the intuition in our head, right? So the most common thing, okay, perhaps the most important scratch work we should always be doing when studying the theory of real numbers, the Dedekind, and all of that, is to constantly draw line segments. Okay, this is an S. Even though we don't call it the set of reals, we try to mimic the properties. Right? And here we have a set E. I draw an interval just as an analogy. Okay, in reality, E can be any bounded set of S. Okay, so we want to define the supremum here. Okay, and everything that is above the supremum are upper bounds. And this is the infimum. So we wish to capture these ideas in words, in symbols. Okay, what's going on with Word? Okay, alpha is the infimum of E. Alpha is the infimum of E. So just to make sure everything is cleared up, the greatest lower bound, and or the infimum. Okay. Okay, we will take no prisoner when it comes to logical gaps. Okay, anything that is left undefined is unacceptable. So imagine we're trying to write code. Okay, if there's a function that we fail to define, the code just won't run. Okay, unless in this case, however, in this case we don't have a compiler that checks for us, so we have to be extremely careful here. So here we have the notion of order set, and we defined the supremum infimum of a subset. Okay, so now these are just terms, terminologies. That's it. But here we want to have the main property that we want. We want to have the so-called least upper bound property. Definition. We say that an ordered set S has the least upper bound property or LUBP if a set is not empty and is bounded above, then it has a supremum. If E is a subset, if for every subset E, for every non-empty subset E of S, okay, and such that E is bounded above, E has a least upper bound in S, i.e. the soup, i.e. the soup of E exists and is in S. Okay. We say that as order set has the least upper bound property if this is true. Okay. So we want the Dedekind cut to have this property. So I'm not even in the stage of defining arithmetic operations yet. Okay, I want this to be true. I want the least upper bound property to be true. Because if the least upper bound property is true, then we can have a few immediate consequences that are well known to us. For example, if you have the least upper bound property, we can you also need the arithmetic rule. Sorry, if you have the least upper bound property and the usual rule of arithmetic, you can have decimal expansion, for example, the usual decimal expansion for the real. So this is absolutely crucial here. So of course this list of this wish list is incomplete, right? This wish list of the desired properties of the real numbers is incomplete here, but we will just leave that for now and go back to Dedekind's cut. Okay, so how does Dedekind connect to all of the things we just talked about? So Dedekind's cut. And when we were reading Whittaker and Watson, a cut has two classes, right? I always find that to be a little bit redundant because it is already mentioned in the text that, for example, the cut for the square root of 2 is what? The right class consists of positive rational numbers whose square exceeds 2, and the left class is just the other rational number. So basically the complement. If you have the right class, you have the left class. So why bother always writing a pair, right? That's not very efficient. Even though, I mean, I guess it doesn't hurt, right? But as far as definition is concerned, you just need one class, and the other class is already determined. So for that reason, we'll just define one section as the Dedekind's cut. Okay, so assume that Q, the set Q, exists. Okay, we assume that Q exists, and the usual, along with its usual arithmetic rules and also order relation and the order relation. Okay, we assume Q is something that is already settled. Okay, and then we try to construct R from it. Right. So what is a cut? Definition. We don't want to use the word interval because I have been using that, right? I've been using the word interval. However, the interval is already considered to be such a well-used term, right? When you talk about an interval, you're talking about a set of reals already. So we want to avoid that term. So how do we avoid that term? I want to talk about the set of all rationals less than something or greater than something, right? Between a certain range, basically. So let's define a cut. A cut is a set, is a subset of Q. Is a subset of Q. A cut is a subset of Q. First we have that, but we still need to have a bunch of properties. Remember in the Whittaker and Watson, they said a cut has to be a non-empty set, right? Well, it said that one of the classes, L class and R class, has to be non-empty. Well, so I will only define the left class here. So with the following properties. I need, let's give it a notation. A subset, let's give it a notation, say alpha. Okay, alpha is not empty. Okay, that's part of the definition of a cut. And also, alpha is not the whole set, right? Because if alpha is the whole set, then the other piece in the original Dedekind series is empty. We don't want that either. So alpha does not equal to the empty set or Q. We want to leave room on both sides, basically. Okay, and we wanted to capture the idea that a cut is a sort of a semi-interval, right? But we can use the word interval. So let's just say if a number if a number p is in, if p, which is in alpha, and if p is in alpha and q is in big Q, with Q is less than P, then Q must belong to alpha. So this is saying that every rational to the left of P belongs to the same cut. Okay. All right. And also, we want to exclude, I mean, this is just, once again, our choice. We want the left part to be always an open interval. Open interval, quote unquote, okay? I don't want to have the left piece to look like something like minus infinity to 1. I don't want that. I don't want that, okay? So I want the left class to never have a greatest element. So let's put that into the definition. So if P is in alpha, so if P is in alpha, let's say, then there is some other. Then there exists R in alpha with P is less than R. So that's a cut. So that's a cut in our formulation. We just want to keep the left class, because if you have the left class, the right class is simply the complement. Okay. So that's a cut. So basically, three, we want to mention that there is no greatest element. Alpha has no greatest element. Okay. So immediately we can deduce something from 2. Proposition. Based on this definition of a cut, we can immediately deduce something. Well, if and by the way, let's just for clarification, we will denote letters P, Q, R, and such be members or be elements of Q. So these are rationals. And we will denote and letters alpha, beta, gamma, and so on. Beta, gamma, and so on be cut. Okay. Proposition. If P is in alpha, and Q is not in alpha, what does that mean? That means Q is in the right class, right? In the R class, in the Whittaker and Watson. Then P is less than Q. That's our first proposition. Should be very easy to prove. Let's prove that. Suppose for a contradiction that P is greater or equal to Q. We consider 2 cases. Well, we consider 2 cases. Case 1, P is equal to Q. If P is equal to Q, then then Q is in alpha. And Q is in alpha, contradiction. Okay. case 2, P is not equal to Q, then by one of the order axiom, trichotomy, by the trichotomy axiom of order, and by the trichotomy axiom of order, P must be greater than Q. So P is greater than Q. Well, but because of property number 2, Q is less than P, Q must be in alpha. By property 2 of cuts, Q is in alpha, which is again a contradiction. So this is very easy. So therefore, in either case we have a contradiction. That means P is less than Q. QED. All right. Okay. So that's our very first proposition. I'll try to use a different font for underline. Okay. Okay. All right. So there's that. The next proposition, I want something like this. So if R is not in alpha, and R is less than S, so that means R is in the right? R is in the right class, and S is even greater than R, then S cannot be in alpha either. Okay, so I want this proposition. Then S cannot be in alpha either. Okay, so let's prove that. Okay, so should we use contradiction? No, because proving something that is not in a set, it's natural to use contradiction. Suppose for a contradiction that S is in alpha. Right, since R is less than S, by the property 2, R is in alpha, which is a contradiction. Once again, the proof is very short. But that's the idea. We wish to dissect a massive series. I mean, it's not that massive, but anyway, a series into digestible bits. Okay. By property 2 of cuts, R is in alpha. No, this is a contradiction. So we're done. Okay, that's the next proposition. Once again, it's very easy. Okay, so cut is now defined. We want to define an order relationship for cut, right? So we want to define an order relationship between cut. We just defined cut. How do we compare them? Definition. We say that by alpha less than beta, we mean alpha is a subset of beta. Okay. Actually, we need to emphasize it's a proper subset. By the way, if I simply write this just means subset. I don't usually do subset equal, but it's possible. But here, I want to emphasize that if alpha is less than beta, we mean that alpha is a proper subset. So I need not a relation that indicates that. Do we have a not equal sign underneath here? If not, we'll just use words. Okay, that's what I'm trying to think about. Alpha is a proper subset of beta. This is a definition. So we define order. So we define order, okay? Now we have an order. We want to verify that the set of cuts. So now by doing that, the set of cuts become an ordered set. This or how should I put this? Now, the set or the collection. We usually don't say the set of sets, okay? Because a cut is already a set. We say a collection or family just for linguistic reasons, okay? The collection of all cuts is an ordered set when equipped with the relation, the order less than, okay? First, we have to verify this is an order, right? This is first have to be an order. Actually, you know what? Let me delete this sentence. This is a definition, proposition. The proposition says this is indeed an order. Okay. Did I delete that? Okay. I want to make that a proposition. Proposition, not part of the definition, okay? The collection of cuts is an ordered set when equipped with a set order order less than. The proposition is the less than we just defined is an order. The notion of defined above is indeed an order. So we will have to verify the two properties, trichotomy and this. Okay, so there might be a source of confusion because I already wrote less than, right? That's just the order relation from Q, right? That's just the order relation from Q, but I can't be bothered to write a subscript Q every time I compare two rational numbers. So be very careful what exact order we're using. Here I can talk about less than because I'm just using the order relation on Q. It's just the usual notion of two rational numbers less than or greater than another. Okay, but here alpha less than beta, this is a new notion. Even though the symbol is the same, they pack different meanings. Okay, so that's why we need to verify separately that this is indeed an order. Okay, let's just put the definition down here and see what we need to do. Proof. We need to verify the two properties. All right. So we let alpha and beta be two cuts, I guess, right? And we need to show that exactly one of the following three is true. Actually, 2 would be easier to verify. The transitivity is easier. So let's first verify the transitivity. Okay, let A be less than beta, and I think we're kind of running out of time, but we will finish proving the least upper bound property. Okay, so if you wish to stay, then my original plan was to stream for 2 hours, but if you wish to stay, you're very welcome. So the transitivity says let alpha be less than beta, and beta be less than gamma. Okay, we need to show alpha is less than gamma. Of course, this is completely trivial because the notion of proper subset of is transitive, right? So okay, so here we can just write this means, or by definition, this means that alpha is a proper subset of gamma, and beta is a proper subset of gamma, right? So need to show this is immediate, since alpha is a subset, proper subset of gamma. All right, the transitivity part is done. Okay, but we still need to prove trichotomy. Okay, so let alpha and beta be cut. How do we prove a statement like such? Exactly one of the following is true. How do we approach that? We need to prove exactly one of the following is true. We need to show. You know what? Let's write that down. Need to show. So exactly one of the following is true. Alpha less than beta. Alpha equals to beta. And alpha is greater than beta. All right. So we want to show exactly one of these is true. Okay, if alpha and beta are the same, the next two has to be false, right? So if alpha is equal to beta, let's see, how do we make this a bit easier to say? It's a bit easier to communicate, so to say. Need to show exactly one of the following is true. What's the opposite of that? The opposite can be none of this true, or more than one is true. Right. So, well, obviously, I want to say that it has to be the case that at most one is true. You cannot have more than one being true. Let's say at most one of the three statement can be true. Indeed. Alpha less than beta and alpha greater than beta cannot be both true, because alpha, why do I write A? Alpha cannot be a proper subset of B, a proper subset of beta, and at the same time, beta being a proper subset of A. These two cannot be both true. And if, let's say, if two among them are true, they cannot be alpha less than beta and alpha greater than beta. As alpha is a subset, proper subset of beta, and beta is a proper subset of alpha, is impossible. Okay. So they cannot be. Sorry, they cannot be. Um, they cannot be the first two either, right? Because this is literally saying alpha is a proper subset of beta, so it cannot be equal to beta. Since alpha less than beta already implies alpha is not equal to beta. Okay. Um, similarly, alpha greater than beta and alpha equals to beta cannot be true simultaneously. Okay. Okay. So at most one of the three statements can be true. At most one. But now we show one of them has to be true. For that, let's assume nothing is true. So, or let's say, suppose the two fail, then the last is true. That proves at least one is true, right? So now we say we now prove that at least one holds. To do so, we assume the first two fails. Okay, we first assume the first two fail and prove the third is true. Okay, so well, since alpha less than beta is false, alpha is not a proper subset. Is false. Alpha is not a proper subset of beta. Okay, and since is not a proper subset of beta, well, that means two things can happen, i.e. alpha is equal to beta, or alpha is not a actually since let me erase that. If the two statements are false, that just means alpha is not a subset of beta. That is, alpha cannot be a proper subset, alpha cannot be equal, that means alpha is not a subset. Okay. Then, if alpha is not a subset of beta, that means there is something in alpha that is not in beta. Okay. This implies there exists some p in alpha with p not in beta. We wish to prove that. Hang on. To do so, we first assume the first to fail. That is, alpha is not a subset of beta. Okay. It remains to show that the last is true, right? It remains to show that alpha is greater than beta. That is to say, beta is a subset. Beta is a proper subset. Proper subset notation. Beta is a proper subset of alpha. We need to show that. So let since we already have beta is not equal to alpha, it suffices to show beta is a subset of alpha. Okay. So now let's use the element chasing technique for proving set containment. Let P to be in beta. Let P be in beta. Oh no, I cannot use P. P is already occupied. So let's use Q. If Q is in beta, okay, we may need to draw a picture to help us sync. Okay, so there exists alpha and beta are not the same. I want to prove beta is a subset of alpha. Beta should be here. Alpha should be here. I want to prove this. Beta is a subset of alpha. So there is something P which is in alpha and not in beta. We know that. So Q is in beta. I want to prove that Q is also in alpha. I think we might need to use one of the properties of the cut. The properties of the cut says if P is in alpha and Q is less than P, then Q is in alpha. Exactly. That Q is in beta. Since P is not in beta, we have Q is less than P, right? Because we proved this proposition earlier. We have this proposition. If P is in alpha and Q, let's put that down. Here I have P is not in beta. P is not in beta and Q is in beta. P is, sorry, I mean there exists P in alpha and P, hang on, there exists P in alpha, right? And P is not in beta. It remains to show that beta, alpha is greater than beta, that is, beta is a proper subset of alpha. Since beta is not equal to alpha, it suffices to show that beta is a subset of alpha. I let Q be an arbitrary element in beta. I need to show Q is also in alpha. Q is also in alpha. For that, I want to use property 2. So I need this condition. I need Q to be less than P. How do I get that? Yeah, since P is not in beta, since P isn't, yeah, that's the proposition. I think we might need to quote this because next time we look at it, we might get confused. So let's call this proposition 1. Proposition 1. This is proposition 2. Okay, so Q is in beta, P is not in beta, therefore P is less than Q. This is proposition 2. Okay, and we underline it just to make it more obvious. Okay, so that's indeed correct. And then by property 2, by property 2 of the cut, we have the two conditions satisfied. Q is in alpha. Yeah, so we have Q is in alpha. So look at what we have done here. We start from letting Q be an arbitrary point in beta, we show that Q is an alpha, and therefore, thus, beta is a subset of alpha as needed. Okay, so this is the order relation verified. Proposition 3 is now proven. Defined above is indeed an order. Transitivity and trichotomy are proved. Okay, nice. Okay, so now that we have verified this is indeed an order relation, okay, we don't need this anymore. So the collection of all cuts is an ordered set when equipped with the order less than. So this is safe. Okay, and now we wish to prove the least upper bound property. Okay, as the finishing task of this live stream. The collection of all cuts. The collection, let's just call that R. This is very suggestive notation. The collection R of all cuts is an ordered set. Okay. And so far R only has an order. Eventually R will have addition, multiplication, and order. So far R is only an ordered set. Okay. We're adding features iteratively. Okay. So now this ordered set has the least upper bound property. We wish to show that. Proposition, or actually let's call that a theorem, because having the least property, it deserves the title of a theorem. Okay, the ordered set R was equipped with a less than. This ordered set has the least upper bound property, LUBP. Wish to prove that. Okay, so what does the least upper bound property say? The least upper bound property says if a set is bounded above, now is non-empty and is bounded above, then it has a supremum. Then it has a supremum inside the set S. Okay, so for that we assume say E to be a subset of S, or A to be a subset of R, okay, and assume that A is bounded above. And of course here A being a subset of R is a bunch of cuts. Proof. Okay, so assume A, which is a subset of R. Okay, so here everything must be understood according to our own definition. R is a collection of cuts. So A is a collection of cuts. R is a collection of all cuts. Right? A is a collection of cuts. Assume A is a subset of R, such that A is non-empty. It contains at least one cut, and A is bounded above. How do you understand bounded above? Well, using the order relation we just defined, is bounded above. Okay. Assume, need to show what? Need to show sup of A exists. Exists meaning it is in R. Okay. Of course, in most elementary analysis courses, the least upper bound property is treated as an axiom. And then we prove a bunch of other things like the monotone convergence theorem from it. Right? Now, what we're doing is to prove the least upper bound property as a theorem, because we defined explicitly what the set R is, not as an axiomatic object. Right? Because the whole point is to show that the axioms are indeed self-consistent. Right. So here we have to actually prove the least upper bound property as a theorem. Okay. So let's go. We need to show that the sup of A exists and isn't real. Okay. And then we must explicitly construct the sup. Right? So that's how you show existence. A is bounded above. How do we define the sup? Remember, here the order relation is essentially set containment. How do you find the biggest set? Well, by forming unions. Right? We can take unions to get bigger and bigger sets. Right? So simply we take gamma to be the union the union of A, or shall we put, let's write it this way, the union of alpha in A of alpha. I know this looks a little bit weird, but basically you take every cut in A. A is a collection of cuts, which are sets of rationals. You take the union of them. Right? That should bound everything in A, right? So it's clear that it should be an upper bound, because every member in A is contained by gamma. So what we do, we take gamma to be the union of all the alpha in A. We will prove that. We claim that. Let's claim. We claim gamma is in R, and gamma is the sup of A. What does gamma is in R mean? Well, gamma is in R. R is a collection of all cuts. So basically, we need to prove gamma is a cut. Gamma is a cut. So we need to prove gamma is a cut. That's essentially. Okay, let's put that here. So this is the first paragraph. Okay. Need to show gamma is a cut. What's wrong here? Okay. Need to show gamma is a cut. So what's a cut? Well, here's the definition of a cut. Let's go. 1, 2, 3. This is the definition of a cut. So let's check 1, 2, 3. 1, is gamma empty? It can't be. A is not empty. So the union of all the elements in A cannot be empty. Since big A is not empty, if A is not empty, then gamma, then it has at least one element. Then A has at least one element. Which is a cut. And thus, gamma being the union of all cuts in A, being the union of all cuts in A, is not empty. Okay, can it be all the reals? Oh, sorry, can it be all the rationals? And that can't be true either. That can't be true either, because it is bounded above, right? So let's see, how do we argue that it is not the whole rational? Okay, let's add a sentence here. A is bounded above. Say, with upper bound beta. Says with upper bound beta. So, okay, right. Since beta is an upper bound for A, that means every set A, every set alpha in big A is properly is less than or equal to, right? Is less than or equal to beta. Okay, so we need to show that it is non-empty. We already showed that it's non-empty. It remains to show that gamma is not the whole Q. So, and I gotta feed my cat. You can probably hear her in the background. I'll be back in like a minute. All right, I'm back. Okay. So it remains to show that Q is gamma is not the whole of Q, since for any alpha in big A, alpha is less than or equal to beta. Right? That's the definition of upper bound. That is, alpha is either equal to beta or alpha is less than beta. So i.e. alpha is less than beta or alpha is equal to beta. When alpha is less than beta, that means alpha is a proper subset of beta, i.e. alpha is a subset of beta. Right? Okay. So this is what the upper bound means. This is what the upper bound means. Actually, this immediately implies that the union must be a subset of beta. This implies gamma being the union of all cuts is a subset of beta. Okay? So gamma is a subset of beta, and since beta is a cut with an upper bound, an upper bound is an element in R. So beta itself is a cut. The upper bound, remember when we define upper bound, an upper bound is also an element in the same order set. When we define upper bound, where's the upper bound? Yeah, upper bound is a element in the order set. The order set here is R, the set of all cuts, right? Since beta is a cut, it can not be the whole of Q. So and gamma is only a subset of beta. Gamma cannot be the whole Q. And thus gamma is not the whole Q. Right. So that's one done. And we need two. Okay, so need to show gamma as a cut. So let's assume we need to assume the if part and then prove the then part. Okay, if P is in gamma and Q is in Q, which is literally copying the if part with Q less than P. Okay, need to show Q is in gamma. All right, so that's what we need to do. So how do you show that Q is in gamma? Well, gamma, what's gamma? Gamma is the union of all the alphas. That is to show, need to show Q is in the union of all the alphas. If it's in the union of all the alphas, it means Q is in at least one alpha, i.e. Q is in alpha for some alpha in big A. Right? That's the meaning of union. Okay, so how do we find such alpha then? Well, we have P is in gamma. Since P is in gamma, we didn't use that yet. Since P is in gamma, then P is in at least one of the, let's call it alpha 0 for some alpha 0 in A. Okay. Okay, since P is in alpha 0, and now we have Q is less than P. Since Q is less than P, then by the second property, by property 2, of cuts, okay, by the property 2 of cuts, the we have Q is in alpha 0. Okay, so that's the and we're done. Q is in alpha 0 as needed. We need to show Q is in some alpha, and that's just alpha 0. So as needed. So property 2 is verified. Property 3. Property 3, if P is in alpha, there exists R in alpha with P less than R. Namely, alpha has no greatest element. That is, we want to show gamma has no greatest element. How do we do that? If assume P is in gamma. There's someone who commented that unfortunately that person does not understand what I'm doing. Perhaps I'm assuming not in a advanced, so to say, in a you don't need to know a lot of formula. You certainly don't need calculus to understand this. There's no derivative or integral. What I think, if most likely, if someone does not understand what I'm trying to do, is perhaps not having exposed to formal proof writing, like if you see a sentence, so to say, a statement, and you want to prove something exists, you actually need to construct such an example, right? Here, our main goal is to prove the soup exists. So that's why we first constructed a candidate and then verify. This is actually the soup and it's also in R, right? So here we're doing the in R part, and then we're doing the soup part. Okay, so all right, so assume P is in gamma, so we're just trying to just copy paste the definition of the third definition. We're assuming the if part. Need to show there exists R. I need to show there exists an R in gamma such that P is less than R. Namely, gamma has no greatest element. Okay, so what do we do? Start from the assumption. Since P is in gamma, we did that earlier, right? So there exists an alpha 0 such that alpha 0 contains P. By the assumption P is in alpha 0 for some alpha 0 in A. Okay, that's the assumption. So we want to show that there exists another element greater than P. Well, alpha is a cut. Since alpha naught is a cut, by property 3. Of cuts, P is in alpha naught. There exists R in, let's call it R naught to emphasize this comes from alpha naught. Can there exist R naught in alpha naught with P less than R naught? The thing is, R naught has to belong to gamma as well, because gamma is a union of all the alphas, right? Since gamma is the union of all cuts in A, and R naught is contained, R naught belongs to gamma, right? So basically we're done. Well, we found an R in gamma with P less than R naught, right? So we're done, and we're done as needed. Okay, so this means that gamma is indeed a cut. That's proven. Okay, so we don't need this anymore. Okay, and then we need to show that gamma is equal to the soup. Let's go. Is gamma is equal to soup? How do you prove something is a soup? Well, first you need to show that it is actually an upper bound, and then you prove that's the least upper bound. Okay, so let's get started. So proving that is an upper bound is very easy, because the union of all sets cannot be less than or less than any of the sets taking part in the union, right? So so for that we need to show gamma is an upper bound. Let's say we need to show 1, gamma is an upper bound, and 2, gamma is the least upper bound. All right. Okay. Upper bound of A. Okay. So let's prove 1. Well, we just pick an arbitrary element. This is immediate. Actually, this is immediate, since for any alpha in big A, alpha is a subset of the union. Is a subset of union, i.e. alpha is less than or equal to gamma. All right, so that's easy, that's done. How do you show that it's the least upper bound? So to prove something is the least upper bound, we can pick, let's say, any set, any set, let's say delta, that is less than gamma, and prove delta is not an upper bound. Anything less than the claimed least upper bound is not an upper bound. No, then we're done, right? So let delta to be less than gamma. This means that delta is a cut, and delta is a proper subset of gamma, i.e. delta is a cut, and delta is a proper subset. I need a notation. I don't know how to type this, so I have to copy this every time I use it. So delta is a proper subset of gamma. Need to show delta is not a upper bound, is not an upper bound of A. How do you show something is not an upper bound for A? Well, you need to exhibit something in A that is greater than delta, for which we need to exhibit an alpha in A with alpha greater than delta. Okay, so that's our task. How do we do that? Well, since delta is a subset of gamma, okay, since delta is a subset of gamma, is a proper subset of gamma, there exists something. Remember, these two are both cut, and delta is a proper subset of gamma. There exists let's say P, that is irrational. Okay, there exists a P in gamma with P not in delta, not in delta. Okay, so this is what we can get from the assumption. And how do we, based on this fact, construct a cut that is greater than delta? Since P is in gamma, well, since P is in gamma, P is in some alpha naught. Or some alpha naught in A, right? Okay, so P is in alpha naught and P is not in delta. So that means everything in delta is less than not everything So that means delta is contained in alpha naught. That's what I was trying to say. But let's prove that. We claim delta is less than alpha naught. If that's done, if we can prove this, then we're done. Right? Claim delta is less than alpha naught. Indeed. Okay, for any, let's say q in delta. For any q in delta, q is p is in for any q is in delta. What we have here? So we have p is not in delta, but q is in delta. So we have p greater than q. Property 2, right? Actually, that's proposition 1. That's proposition 1. So that's proposition 1. By proposition 1, proposition 1, let's put that down, okay, just to make sure we're not hand waving. This is proposition 1. If p is in a cut and q is not in that cut, then p is less than q. Right? So here we have q is in delta, but p is not in delta. Right? Is in some cut, q is in some cut, but p is not in the same cut. That means q is less than p. Okay. And and then we can use the second property of the cut. Here we have definition of the cut. Here we can use the second definition, the second property of the cut. Right? We have p is in alpha naught, and q is less than p, so q is in alpha naught. Since p is in alpha naught, by property 2, property 2 of cuts, not alpha 2, okay, alpha naught. Q is in alpha naught. So what do we have? We have for any q in delta, q is also in alpha naught, so therefore delta is a proper subset. I said proper because we already have an element that is in alpha naught, but is not in delta. So delta is a proper subset of alpha naught, i.e. delta is less than alpha naught as claimed. Okay, so we've done all of that. So here the proof is now finished. Gamma is indeed the sup of A, right? So we've done these two parts. We claim that gamma is an alpha, that's proved. Gamma is a sup of A, that's proved. So therefore, the Dedekind cut has the least upper bound property. And that's done. Okay, so that's only a very small part in the theory of Dedekind. So if we want to spell out all the details, this is actually not a small task, right? So here we only handle the order relation. We define what is an order, in general. We define what is an order in general. We define the least upper bound property, which is actually the distinguishing feature between the real and the rational. Okay, and then we see, okay, how can these properties be realized, right? So let's define a cut constructed from the set of rationals, and then define a concrete relationship between the cuts. What do we mean by one cut being smaller than the other? After that's done, we need to verify this is indeed an order. Okay, so therefore we now have an ordered set. We call the ordered set R. It's a very suggestive notation. And then we verify that this ordered set we just created has the least upper bound property, which we just done proving. Okay, so next up, we need to follow the same procedure that in Whittaker and Watson, over in modern notation of how do we define arithmetic operations, so to say. How do we define add, and we need to check addition, subtraction, and basically addition and multiplication have the usual property that we desire. And also, the order relation interacts well. Order relation interacts in the usual way with the arithmetic operations. Okay, so yeah, don't be frustrated that we only finished one section, right? We did finish reading this section. Okay, we didn't. We're not fooling ourselves. Okay, we did read the full section on the Dedekind theory of irrational numbers. However, I think it is fair to say that not every detail is spelled out. Okay, so we need to do that ourselves and in a modern way. Okay, that's it for today's live stream. I hope everybody had a great time. I mean, I certainly did. If you have any suggestions, please let me know. And actually, I'm wondering if you guys want to have some kind of Google Drive, so to say, so I can upload all the things we've written in the live streams for future reference purposes, if that's helpful. So I'll try to work on that, and we'll see you next time. Okay, and next time probably will be I can't do another stream this week. Right now I'm still kind of busy, but I'll try to, as I mentioned earlier, I'll try to put out almost a short each day. I think that's not a huge commitment, but in the summer definitely we'll have more time with the live stream. Okay, thank you very much for watching, and I hope everyone have a very good evening. I mean, it's evening right now in Eastern Standard Time, and I'll catch you next time. Bye.